3.6, the chain rule, part 2. I'd like to continue the discussion about the general power rule by doing another example. What about this problem? I've got y equals the square root of 5x squared plus 1. The first thing I'm going to want to do is I'm going to want to make my problem look like u to some power. And so instead of using the radical, I use exponent notation. Then, as I did before, I identify what is my inside piece. Okay, so my inside piece is 5x squared plus 1. And I'm now ready to use the chain rule. I bring down the 1/2, and then I've got my inside piece is now to a new power of 1/2 minus 1. Then I need to find the derivative of what's inside. So just to recap, the derivative will be 1/2 times the inside to the 1/2 minus 1, all of that times the derivative of what's inside. Now the negative exponent is not in good form, so I would just rewrite my y prime this way. And then of course 10 over 2 is 5, and also you can change over to or back to radical notation. Okay, let's switch to compositions that involve a trig function. Suppose we have y equals sine to some polynomial like x squared plus 5. As before, we name the inside function, and so y equals sine of u, where u equals x squared plus 5. And as we did before, let's find dy du and du dx. Well, dy du is cosine of u, and du dx is 2x. And so now, to find dy dx, I'll just find the product of dy du times du dx. All right, so what is the product? It'll be the cosine of u times 2x. What you want to do next is replace u with what it is. It's x squared plus 5. And so you get cosine of x squared plus 5, all of that times 2x. And generally, we like to put the 2x out in front so that we don't accidentally bring it into the cosine where it doesn't belong. Again, like we did before, I'd like to streamline the process. You know all your trig rules. The derivative of sine x is cosine x, the derivative of tangent x is secant squared x, and the derivative of secant is secant tangent. Well, we're going to generalize this using the chain rule. If it's the derivative not of sine of x, but sine of u, where u is some function, the derivative is going to be the cosine of that function times the derivative of that function. And the same idea with tangent and secant. And of course, you can expand this to cosine, cotangent, and cosecant. Change all of your trig rules into general trig rules. Okay, let's go do another example. Suppose f of x equals tangent of 9 minus x squared. I'm going to use the general trig rule for tangent. The derivative of tangent is secant squared. So my inside is 9 minus x squared, and so the derivative of that is negative 2x. Using my general chain rule, I'd have the derivative is equal to secant squared of the inside times the derivative of the inside. And then, of course, it's better if you bring that negative 2x to the front and rewrite it this way. We've been using what I call version 1, or I think the book calls version 1 of the chain rule. There's another version of the chain rule, version 2. I'm only showing you this version because you might prefer that version, version 2. Version 2 has more of an emphasis on the idea that you're dealing with a composition. So going back to a problem that we just did, if I want to find the derivative of sine of x squared plus 5, I define my inside function to be g of x equals x squared plus 5. And so what I have is a composition. F of x is f of g of x, where g of x equals x squared plus 5. And then using version 2 of the chain rule, I just have that the derivative is cosine of g of x times the derivative of g of x. G of x, I just put in what g of x is, and I put in what the derivative of g of x is, and then I clean it up. Personally, my preference is version 1 of the chain rule, and you'll find that I use that primarily. All right, one last example. Oh, no, I think we're out of time. All right, take care and have a great day.